Good evening, Bearcats. It's Mrs. Suderman
And Mrs. Zorn
with your evening flipped instruction.
Guys, it's Mrs. Suderman for example number 1. We have the area of a parking lot is 600 square meters. A car requires 6 square meters and a bus requires 30 square meters. The attendant can only handle a total of 60 vehicles per day. If a car is charged $2.50 per day and a bus is charged $7.50 per day, how many of each type of vehicle should be accepted to maximize daily income? And it says to scale each axis by 5, and you'll see that I've already done that. I also went ahead and labeled the axes cars and buses, which kind of gives you a hint of this next thing we're about to talk about. Just like we did before on the solving linear inequalities, we always want to define our variables first. Linear equations. We always want to define the variables first. And the variables should answer the question, which here is how many of each type of vehicle. So X and Y should stand for how many types of cars. So X will be the number of cars, and Y would be the number of buses. Okay, now we need to figure out the system of inequalities that we can get from the information provided in this problem. Because this is a real-life scenario, the first two inequalities that we should define have to do with the number of cars and number of buses. Because this is real life, we cannot have a negative number of cars and buses, so we should make sure that they are always positive or greater than or equal to 0. So the number of cars, which is X, must be greater than or equal to 0. And then Y, which is the number of buses, must be greater than or equal to 0 as well. So those are the first two, and they're easy, but make sure you have those because that makes this problem make sense. Okay, and now we know that each car requires 6 square meters and a bus requires 30 square meters. Altogether, the parking lot is 600 square meters. So that tells us the space between the cars and the buses must add up to no more than 600 square meters. So we have 6 square meters times the number of cars, X, plus 30 square meters times the number of buses, Y, that must be less than or equal to the number of square meters in the parking lot, which is 600. And then also we know that the attendant can only handle a total of 60 vehicles per day. Therefore, the number of cars plus the number of buses must be less than or equal to 60. Alright, so in just a moment we're going to graph all of these inequalities, but maybe what we should do first is make sure that all of these are in a form that makes it easy for us to graph. So let's look at the 6x plus 30y is less than or equal to 600. So if I'm trying to get y by itself, I'm going to subtract 6x from both sides. And then I'm going to divide every single thing by 30. So I get y is less than or equal to, negative 6 divided by negative 30 is negative 1/5 x, and then 600 divided by 30 is 20. So there is another inequality. So we've got x is greater than or equal to 0, y is greater than or equal to 0, and now we've got this one, which will be easy for us to graph. We have one more, and this one won't be as bad, but we need to get y also by itself. So I'm just going to subtract x from both sides. So we get y is less than or equal to negative x plus 60. And there's our fourth inequality. Alright, so let's go ahead and begin graphing these. The first one, x is greater than or equal to 0. So let's just graph the line x equals 0. Well, that is along the y-axis. So let's draw a vertical line along the y-axis. Let me change my color here so you can see it. Okay, so there we go. And then we also have y is greater than or equal to 0. Just going to be along the x-axis. And because these things are inequalities and they're not just lines, we need to distinguish where the shaded region would be. So because x is greater than or equal to 0, it's not just the values on this line, it's all of the x values that are greater than or equal to 0. So instead of shading all over the paper, for now I'm just going to draw some little arrows to remind me which side of this line I'll be shading. Also, y is greater than or equal to 0 means the y values included will be above or equal to this line, so I'm putting arrows to note that as well. Okay, the next line that we have is y is less than or equal to negative 1/5 x plus 20. 20 is our y-intercept, so we can put a point there, and our slope being negative 1/5, because our scales on both the x and the y-axis are the same, we can actually count down 1 over 5 just like we would normally if the scale were by 1. So down 1 over 1, 2, 3, 4, 5. Down 1 over 1, 2, 3, 4, 5. And so on. And we can connect these points to get a line. Like that. For this one, it says the y values are less than or equal to this line. So that means underneath is where we're going to be shading. A good way to determine, like we talked about yesterday, in yesterday's video, which side of the line we're going to be shading is to test the origin, because it's an easy point to check. So if we plugged in the origin, which is at 0, 0, and for y and x, we get 0 is less than or equal to 20, which is true. So because the origin is true for this inequality, we shade on the side of the origin. So here the origin is below the line, so we're going to shade below the line. We also have y is less than or equal to negative x plus 60. So our y-intercept is at 60. And again, our slope is negative 1, so we can go down 1 over 1 like we would as if the scale were by 1. And so on, and we can connect those points as well. Okay, and for this one, again, we are going to be shading underneath, but don't forget you can check the origin. For here, 0, 0 would be 0 is less than or equal to 60, which is true, so we're going to shade on the side of the line where the origin is at. So now we have to figure out where do all of these regions overlap. So what we're going to look for is a region where all of the arrows are pointing to the inside, which is all right here. Okay. Some interesting information about this is now we have 4 corners to this shape that we just made. So they are 1, 2, 3, and 4. The information that we didn't use in the word problem before was about the amount of the vehicles are charged. So a car is $250 and a bus is $750. And we're trying to maximize our daily income. So we've done all of this work so far to figure out how we can maximize the daily income. So what we're going to do is now write the objective function using that information to talk about our daily income. So our objective function, go down a little bit here. Our objective function will be P equals, and that P doesn't necessarily mean anything. I guess you could think of it as maybe it stood for profit, but you could have any letter there, P, Q, doesn't matter. But our money that we have coming in is $250 per car, so 2.5 times X, $750 per bus, so 7.5 Y. And then whenever we know the number of cars and buses we have, we can figure out our income. So because we're wanting to maximize this, let's use these 4 corners from the shaded region that we've had. So we've got the points 0, 0, 0, 20, 60, 0, and 50, 10. And when we plug these x and y values into our objective function, let's go ahead and do that. So here we get 2.5 times 0 plus 7.5 times 0. Well, that equals 0. So that's not likely to be our maximum income. Let's try the next one, 2.5 times 0 plus 7.5 times 20. That's equal to 150. Then we get 2.5 times 60 plus 7.5 times 0. That also equals 150. And then finally 2.5 times 50 plus 7.5 times 10. And that equals 200. So out of our possibilities here, to maximize our daily income, our maximum income here was $200. Therefore, to maximize our daily income, we should accept 50 cars and 10 buses. Thanks for watching. Stay tuned for Mrs. Zorn's video on example 2.
Okay, kids, here we go. It is going to be number 2, example number 2, when we're going to continue linear programming, and this is Mrs. Zorn. All right, this is about a farmer who has 50 acres for planting alfalfa and soybeans, and he has a maximum of $1,200 to spend on planting. It's going to cost $20 an acre to plant alfalfa and $30 an acre to plant soybeans. The profit for alfalfa, ooh, that's a big word, profit. That's going to have to do with our objective function. For planting, profit will be $250 for alfalfa and $300 for soybeans. And the question is, how many acres of each crop, okay, so we know how many of each crop, should the farmer plant in order to maximize profit? Okay, that's all going to have to do with our objective function. I think it's really important that we know what that objective function is first, so that we are working toward that and not confusing that with what our constraints are. First, let's identify our variables. Okay, we're going to say that alfalfa is going to be our X value and that soybeans is going to be our Y value. And I'm going to go down here and I'm going to go ahead and label my grid. So alfalfa, I'm just going to say down here A-L, F-A-L-F-A. I'm going to put soy on this side just to give myself a little more room on the left. All right, so alfalfa is going to be our X values and soybeans are going to be our Y values. All right, the first thing we're going to do is we're going to go ahead and come up with our objective function. So I really like to come up with that first. So my objective function would be dealing with our profit, and we want to maximize profit. So how do we make money? How do we make a profit? We make a profit because alfalfa, we're going to sell it for $250. So for 250 times X amount of alfalfa, plus 300 for soybeans, $300 times X amount of soybeans. And that's going to be our objective function, and we're going to figure out in a minute what values of how much of each crop could we plant to be able to maximize our profit. All right, the next thing we want to do is we want to write our constraints before we graph. Remember, we talked about before that the first two constraints, because we're in a first quadrant and we're talking about the real world, will be our X values are greater than or equal to 0, and our Y values are greater than or equal to 0, and that puts us in the first quadrant. It's sort of given information, although not given in the problem. It's a constraint that you should always write down because we are in the real world. We're not going to plant negative amounts of alfalfa or negative amounts of soybeans. That would be sort of impossible unless we lived in another dimension. All right. Uh-oh. I don't know what that is. Okay, here we go. Next, let's talk about our other constraints. We have two variables, so most likely we're going to have at least two constraints. The first one says the farmer has 50 acres for planting alfalfa and soybeans. So he has 50 acres. So I would say that if you plant X amount of alfalfa and Y represents the amount of soybeans, altogether it has to be less than or equal to 50 because we only have 50 acres. Next, we're going to talk about the next constraint. So I'm going to cross things off. Look, we've already used 250, we've already used 300, we've already used 50 acres. I do that so that I don't use something more than once, because everything will only be used once. We're left with the cost. It costs 20, it costs 30, and we have a total amount to spend of $1,200. So that's all going to go in one constraint. So alfalfa costs $20 an acre. So 20 times X, And soybeans is $30 an acre, so 30 times Y. And altogether, that has to be less than or equal to $1,200. Okay, and now we've used all of the information in our problem, or at least all the values, and I believe we're done with our constraints. I'm going to go ahead and write that on here. Those are constraints. And the more organized you are in your work, the better. I should have written that above there. All right, the next thing we're going to do is graph. When we graph, then we're going to find our shaded region, or our feasible region, and then we're going to take the intersection points of that feasible region and use those to plug into our objective function, and in this case to figure out which one would maximize, so give us the largest value. All right, so first let's graph. We've already graphed x is greater than 0 and y is greater than or equal to 0. That's already been done. Let's go ahead and graph x plus y equals or is less than or equal to 50. Now, we could go ahead and write this in slope-intercept form. Sometimes you can also graph these. It's important to know you can graph these by x and y intercepts. In this case, that would be pretty easy. I could just graph this x and y intercepts. The x-intercept is when y is 0, and the y-intercept is when x is 0. So if I made my y value 0, if I made this 0, I would have x is less than or equal to 50. So x would be 50, or equal. If I graph the y-intercept, that would be x is 0, and I'd have y is less than or equal to 50, so our y value would be 50. And there's two ordered pairs along our line. So let's go ahead and do that. Oh, please notice that the axis should be scaled by 5. Pay attention on the worksheets and in our tests about our scale values. All right, so if we do that, we have this is going to be at 10, 15, that would be 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, and 80. And the same thing up the y-axis. So this is going to be 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, and 75, 80. All right, so let's go ahead and graph 50, 0, and 0, 50. So we're going to come along here, 5, 10, 15, there's 20, 25, 30, 35, 40, 45, 50. And that would be a point on our graph. And then we're going to graph, okay, so we're going to graph 50, or 0, 50. So there's the 10, 15, 20, 25, 30, 35, 40, 45, and 50 would be right there. All right, I'm going to try to take a straight edge. Let's see if I can find a straight edge. We'll improvise. We'll use a piece of paper. You want to take a straight edge and draw the best line you can. You want to be really careful when you do these. Since this is 50 and 50, you're going to assume your slope is 1. So we could actually just do that. So it's going to just be 1 down and 1 over, and 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 1 down and 1 over. This is a straight, linear, did I mess up? 5, 10, 15, 20, 25, 30, 35, 40, 40. Oh, I did. It should be right there. Okay, be really careful. You see what I just did there. I didn't count my counting off. So label carefully, and then we would have your extra point here. And then you would draw a line to connect those, and it really would be best to use a ruler to make a really pretty straight line. Okay, because that was going to be less than 50, everything shaded would be on the inside. So it would be bound by the axis and that line. So that triangle in there right now is our feasible region. We're going to see what else we're going to figure out in our feasible region. For the next constraint, we're going to take a look at that. Let's go ahead and solve that one for y. And so we would move the 20x to the other side, and we would have 30y is less than or equal to negative 20x plus 1200. And then you would divide everything by 30. And when we do that, we have y is less than or equal to, and the zeros can cancel, so negative 2/3 x would be our slope. And 30 goes into 12, 3 goes into 12 4 times, plus the 0, so plus 40. So I just changed that form to make it a little easier to graph. Our y-intercept would be 40. So we would be at 5, 10, 15, 20, 25, 30, 35, 40. There would be our y-intercept. And we would count our slope at -2 over 3. So down 2 and to the right 3. So from here, down 2, right 1, 2, 3. And down 2 and right 1, 2, 3. And there's a big point right there. Go ahead and finish graphing. 1, 2, 1, 2, 3. And 1, 2, 1, 2, 3. All right, and so there would be our line, and I noticed that this is the big point where the intersection of that line happens. So I'm going to go ahead and just finish drawing in this line to make it. All right, so what we just did is we took that triangle that we originally, and we just chopped off this little part right here at the top. And so now our feasible region, I'm just going to kind of highlight the edges of that. Would go to here, it would come down here, the triangle that we had before, and of course go along the x-axis and then up the y-axis. And it would be everything then in this area. And I'm not going to color it all in, but it'd be in this area right here. So that's our feasible region. But we're interested in the vertices. And so we have vertices here at the origin. We have a vertice here. So at the origin it would be at 0, 0. We have a vertice at 0, 40. We have a vertice at 30, no, sorry. Yes, 30, I was off. 30, 20. And then finally, we have a vertice at 50, 0. All right. And now you find your vertices. You use your objective function. You plug everything back into the objective function. If I plug 0 in for x and 0 in for y, I would have 0. If I plug 0 in for x, I would have 0. So let's just show you that. So this would equal 250 times 0 plus 300 times 40. And when I do that, I'm going to get 1,200. When I plug 30 in, I get 250 times 30, and I get 300 times 20. And when I calculate that, I get 13,500. And finally, I plug in 50, so I have 250 times 50, and I have 300 times 0. And this time I get 12,500. And remember, it asks us to maximize our profit. So we want the one that gives us the most amount, which would be the 13,500. And that would be our ordered pair, 30, 20. And you want to interpret that. So I'm going to go over here, and we would have a max profit of $13,500 when and we're going to plant, and we're going to plant 30 acres of alfalfa, and I'm just going to do a capital A for alfalfa, and 20 acres of soybeans. I'm going to make a big S for soybeans. And that would be it. Okay, that's your last linear program for the evening. Okay, that's the end of our linear programming part 1 for now.
Have a wacky Wednesday evening, Bearcats!